The video course for CompTIA's Network Plus, the N10008 certification exam. My name is Patrick Lohner, and I'll be your instructor on this course. I'm going to start with just a little bit about my background. I've been in the IT industry for about 23 years in various capacities. I worked initially for a training company doing some network technician and network administration while I got my certifications up and then started to teach. I started to train on all the CompTIA courses, A+, Network Plus, Security Plus, and eventually even some others. And I also got my Microsoft Certified Trainer certification in MCSEs. For about 11 years, I broke off and worked on my own as an independent trainer and consultant. And then from there, for the last 4 to 4.5 years, I've been working for a managed service provider. In fact, I worked for 2 managed service providers, one for about 3 years from 2004 to 2007, and then another one from 2018 here to the present. And the managed service providers, that's where I kind of got my most hands-on utilization. Managed service providers provide IT services for other companies that either don't have their own IT or just utilize us for specific projects. My specialties are certainly Windows networks, Active Directory, and Exchange email systems, in addition to the Outlook clients that connect to those email systems. And that now has transitioned to a lot of experience with VMware and Hyper-V, a lot of experience with Azure Cloud and Office 365. And I work on a daily basis either performing network projects and implementations or having service tickets escalated to me. Okay, work a lot with firewalls, routers, and switches as well, on a daily basis. So I certainly feel I am prepared and qualified to help you through this entry-level course into networking. All right, in this chapter, we're going to begin at the proverbial beginning. We're going to talk about network fundamentals, what makes up a network, what's the purpose of a network, the various components that exist there, how they all interconnect with one another, and for what reason. I mean, that's kind of in a nutshell what we're talking about. When we get into the particulars, it's networking models, networking topologies, the actual physical layout, additional components and services that are involved on a network, and network standards, which is going to be a really important part of networking, but one that we don't think about a whole lot. But just the standardization of these products so that they can be used across multiple vendors, multiple operating system types, physical device types, those kinds of things. So we need standardization. But let's begin with an introduction to networking. In this first topic, an introduction to networking, we're going to be just dealing with network fundamentals. As I had just mentioned, a lot of the things that are required in order to have a functional network and its general purpose. So it stands to reason that we should answer the question, what is a network? Some of you are, coming into this for certification, maybe don't have a whole lot of, on-the-job type of experience because you're just trying to get into a career, or maybe you're already in a career and you understand a few of these things and just looking to validate that knowledge through certification. But we want to start with, and we're going to deal with a lot of fundamentals in this course because we kind of assume a ground-up mentality. Which is what CompTIA is assuming. So what is a computer network? It's essentially computers and services that are connected for the purpose of sharing resources or sharing things with one another. Since we have computers that can store data locally, we can have computers that can access data remotely. It's more efficient to have data spread across multiple systems than it is to have standalone systems. Okay, and that's for a variety of reasons. But one of them, for instance, would be just management of systems. The resources are the individual computers, and I can centrally manage them because I have a network. All right, that's one potential. But computer networks are the foundation of communication. A computer network is essentially a bunch of computers connected together, right? So that they can see one another, and presumably so that they can talk to one another. They can communicate with one another. And as soon as you have systems communicating with other systems, then we have applications that can be accessed and utilized across multiple devices. It becomes very, it's a very big part or a big reason for our networks. Now, they're going to vary in type based on various factors, like the location of the connected systems. Are they all in one place, or are they different geographic locations? How big are we talking about? 10 or less computers in a branch office versus 200 computers in a corporate office, that kind of thing. Administrative control. Is it centralized or decentralized? Okay. I also say that with management. They kind of go hand in hand. If I have admin rights on a system, a remote system, I'm going to be able to perform activities or actions on that system that require administrative privileges. If that administrative privilege is coming from that computer only, that would be decentralized. If it's coming from a larger group of computers in the network, then it's going to be centralized. And not only can I access it, but I can also manage it. I can push out policies. I can enforce security controls, etc., to push out applications in order to centrally manage. And they can vary based on legacy and versus modern equipment. In a perfect world, everybody's got new servers or new host and a bunch of new virtual machine servers, virtual servers, and Windows 10 or later on the clients. But working with an MSP, a managed service provider, I don't experience that. I do experience the perfect world, but it's pretty rare, right? Instead, you're often dealing with older operating systems or older network hardware, switches, routers, an older version, less capable of a firewall, that kind of thing. So generally speaking, the vast majority are going to be a mix of legacy and modern equipment. But those are some of the ways that we can distinguish a computer network. Again, its main purpose to allow us to share resources. And regardless of the type of network, all networks are going to have the same components or common components. It can be, of course, different variants of these, but they serve the same general function. The first term that you need to know is node or host. Node and host are really synonymous if they are being used in a question. That's the only time you would find this distinction. If they're being used in a question, then a host has an IP address. A node does not necessarily have an IP address. Okay, just kind of stick that in the back of your mind. That's an unrealistic distinction, but sometimes certification exams make us make unrealistic distinctions. In real life, node host is just a term that somebody decides which one they're going to use. Usually, we're just talking about computers. We could be talking about clients. We could be talking about servers. You could be talking about mobile devices, that are connected to the network, printers, routers, switches, etc. Basically, it's a node or a host on a network. And what was the purpose of the network? To allow those individual nodes to share resources with one another. So when we say resources, we're talking about files, applications, services like domain services, policy management, name resolution for the internet would be another service. Application would be like a SQL database that I get into, or a remote desktop to a server. So remote desktop is the application in order to run other things, accounting applications, payroll applications, etc. And files, of course, we all are probably familiar with the concept of a file that's stored on the network. It's stored on a server so that it is accessible by multiple clients. Now, in the true sense of the word, clients and servers, it's really about the context of the connection. Okay, clients request information, servers provide information. All right, clients request, servers provide. It also has to do with the operating system, but in many cases, they're just kind of, this is sort of an abstract level. You're basically just saying this is the function of this device within this network communication. If we're talking about operating systems, then yeah, we have Windows servers, we have Linux Ubuntu servers, SUSE Linux servers, various other distributions. On client machines, we have Windows 10, we have Windows 11, we have the Mac OS, and we have variants of Linux. All right, those are client operating systems, there are server operating systems, but there's also just that fundamental, how are they talking? Clients request something, servers provide that something. Media, generally storage, is going to be utilized to centralize storage for multiple clients. We can have servers that have multiple disk drives locally, direct attached storage. We can have servers that are connected to storage area networks, which is dedicated high-end storage for client use. We can even have clients connected directly to the storage as well. That would be called network attached storage, and we'll discuss the difference between those two in a little bit. But that's predominantly the media that we're dealing with. The devices are going to be Most from an end user perspective, it's printers. A copier, scanner, that's going to be the device they use on a daily basis. That device can potentially scan documents and send them email. That requires network communication, of course. That's going to be what they're familiar with. Other devices are ones that, as IT professionals, we would be familiar with, and that would be switches, routers, firewalls, any other device that physically connects to the network. All of these are the building blocks of that network. And I did actually skip over something. The network interface card on the node, any device that's connected to the network is going to have a NIC. And that NIC's got actually a couple of addresses that are associated with it. And they provide us a means of network communication. We'll leave it at that because we're going to go into that in more detail later. Now, in terms of standards and just names or acronyms that you have to remember, this is definitely going to be one of them, although it shouldn't be terribly difficult. These are the various categories of networks. Now, the two big categories have always been LAN and WAN. Okay, LAN stands for local area network. WAN stands for wide area network. The key distinction is a LAN is typically a single geographical area. Okay, a single geographic location is a LAN. When you combine multiple LANs by connecting different geographic locations, multi-site business, right? Then you have a wide area network. Okay. Now that's the big distinction between the two. Now the how and the how you get it done, of course, involves different components in the case of wide area network. But we're predominantly going to be dealing with local area network. In fact, other than just kind of this acronym and understanding what it is, CompTIA has chosen to take the WAN topics pretty much off of the 008 version of this exam. So we won't go into a lot of detail. We'll talk a bit more about software-defined wide area networks later, but the rest of these we really won't go into. So LAN, local area network, single geographic location. Then you have variants of that. You have the wireless LAN. A wireless LAN just simply means that instead of physical connections, we're using wireless connections and technology. A personal area network, the name doesn't really give it away other than just to say these are individual devices. So think close proximity. So technically, I have a personal area network between my phone and my wireless headphones. I have a personal area network between my phone and my computer, or my phone and my car. Like technically, those are all personal area network, and they utilize Bluetooth wireless. A storage area network, I had mentioned before with the servers, this is a high-end data storage location. Okay, but there are a couple different SAN protocols, iSCSI and Fiber Channel, that are used, but it is an isolated network between servers and the hard drives, the physical storage that they would be accessing. Wide area network is just a combination of multiple local area networks. So technically the biggest wide area network in the world is the internet, because that's exactly what it is, connecting people, places, things, devices all over the globe. We have some variations of that. You have metropolitan area network, that, as the name implies, is in a city location. Now, it's a bit more to it than that. I mean, a metropolitan area network typically is the government offices of a downtown, of a municipality, and they're all connected. And so it kind of it assumes particular types of connections, often point-to-point wireless, underground fiber, those kinds of things. That would be a true metropolitan area network. So it's multiple locations, but it's still within same area. Same deal with campus area network. They have the distinction because many college campuses, and even business campuses for real large organizations involve actual multiple buildings. And so it's in the same geographic location, but you still have different physical entities. And so you have to get connection between those. Again, wireless, fiber. And so that's what generally designates it as a campus area network. And we have software-defined wide area network as well. SD-WAN. This is using cloud technologies essentially, and the ability to essentially manufacture a wide area network using a single provider with multiple clients wherever they happen to be in the world. So it comes along with cloud technologies, and we'll be talking about that more in the future here, because as I said, that's kind of the one wide area network topic that is still in Network Plus. All right, so earlier we talked about host and nodes. In order to be able to communicate on a network, you have to have a a few things. Once you are communicating on a network, then we call you a host or a node. And the first requirement, of course, we mentioned earlier, and that's the NIC. The network interface card is a connection that generally is going to be a part of the motherboard of your modern desktops and laptops, but in some cases does need to be added via USB or PCI interfaces. And that's true even of modern, where actually, I make those statements. Every laptop I've ever had has had a network card. The one I got a month ago did not have a physical Ethernet jack. So you do have to look at that when you're looking at laptops. Do they actually have it, or do they need a docking station? In some cases, some of the more streamlined laptops, are going to would forego that particular connection. So what a NIC has is a transceiver, which is a transmitter / receiver, and it matches with the network that's being used, and it is used to transmit and receive, to transmit packets, to send information out, and to receive packets in, to receive information in. The term packet just means, it's just a general reference to anything that really is going across the network. Just think of a little package that contains data. And so obviously there are going to be billions and billions of packets that are being sent. The NIC is matched with the media, as we said, in use on the network. So if you're a wireless network, I need a wireless NIC that's capable of transmitting at the same frequencies that the access points are listening on, and utilizes the same protocols that those systems are using. And the same thing goes with a client computer. Okay, if you're connecting to Ethernet, you need an Ethernet NIC. That's a physical wire. It has an RJ45 connector. We'll get into all that good stuff. You'll be able to memorize all of those things. But it's matched to the media. Okay, it's matched to the speed also. So if I connect a device to a network that's 1 gig, but my network card is only 100 meg, then I'm only going to get 100 meg, right? You kind of, as we think about network communications later, we'll see that that smallest point, you're going to be down to those speeds because of that media. So sometimes we have a little bit of flexibility, but we always have to use the same general type of technology. Once I have a physical connection, I need a client as well. So that just means you have to have a network client installed to be able to communicate with the operating systems that are running on servers, which we sometimes call NOS for network operating system. And we have to have that client. So if I'm in a all Macintosh network, I need a Mac. If I am in a all Windows network, I'm going to use a Windows machine and a Windows client. And that's about it, right? Those are really the only two. Back in the day, there was Novell NetWare, and I have seen it once, at least in the last year still. Somehow, some way, it's still out there. But in those cases, you would need like a Novell client. You would need a Unix client if you were going to access stuff off of Unix servers. You would need clients potentially to access anything from a Linux box on a Windows machine. So you do have to be running the appropriate client. Doesn't necessarily mean you have to be running that operating system, but you'll have to be able to have a client that's going to communicate with the server. And the way that they're going to communicate is going to be the protocol. The protocol, you can just think of it as a language that computers, servers, other network devices use to talk to one another. It is more kind of rules and standards that define that communication. But it is just like a language. So as long as you and I can speak the same language, we're going to understand one another. It really is irrelevant if you speak 10 languages and I speak 5, as long as one of them is consistent with both of us, then we'll be able to communicate. Again, some of these things like the network client and the protocol, it was more of a question 15, 20 years ago. And now this has all been pretty much standardized. It's TCP/IP and it's application layer protocols that are going to be able to work with that together because they're largely standardized. And so it makes it easier, right? Generally speaking, we're dealing with Windows systems. If we're not, we're probably dealing with Linux or Mac, but the browser, Google Chrome, Firefox, Edge, Safari, it's consistent in how it's accessing the server. So we have application protocols. So you're going to have lots of protocols. Protocols are very important. There's going to be quite a number for us to actually remember. There are going to be a lot that we need to know what they actually do. So we're going to get into all of that. These are the general requirements. I got to be connected. I have to have a client that interfaces with the server, and I have to be speaking a language that the server is going to understand. Now, in computing, everything's based on the binary numbering system. So unfortunately, we always get to do this, and it's this exercise in math, basically. In networking, the binary numbering system does come up in the form of IP addresses. So IPv4 addresses are 32-bit binary addresses. IPv6 addresses are 128-bit binary addresses. A MAC address, though, is the other address associated with a network card, and it's actually written in hex. Now, it's still a 48-bit binary number, but it's written in hexadecimal. IPv6 addresses, while they're 128-bit binary numbers, they are written in hexadecimal. So therefore, we've got this, this becomes just a worthwhile exercise, because especially when we get into IP addressing, subnet masking, etc., it's very important to understand the binary numbering system. This may or may not be something any of you, that you have used or seen, or just haven't done so since, 8th grade. I don't remember what year we learned about binary, probably before this. So the numbering systems, though, are all the same in that they have a base number. And the base number really determines how you calculate values. In the binary numbering system, it is base 2. The 2 just simply means there are only 2 possible values. Okay? And so there are only 2 possible values, 0 or 1. So they're not really values per se. They're just, it's almost an on-off. And this is why computers use the binary numbering system, because it's very easy to express everything in just an on-off fashion, and represent, of course, each individual bit. Now, the decimal numbering system's the same. It's based on a base number, but the base number is 10. So there are 10 possibilities. If you think about it, 0 through 9. Those are the 10 possibilities. Hexadecimal is base 16, so there's 16 possibilities, 0 through 15. With hex, we have the problem of we have so many possible values that we're into double digits. So how do we actually accurately represent that? So hexadecimal, we use letters. So 10 equals A, 11 equals B, all the way to 15, which equals F. Now, I have this laid out in exponential form, and I'm really doing this not to change the way you think about things, but just so that you see that binary is not really that different. That's the problem a lot of times in trying to understand this, is thinking that it's some foreign concept, but it's not. Binary is the same as decimal, okay? In that if we want to figure out, we're going to use these numbers, okay? So each of these numbers, 1010, 1011, 171, and AB, they're all 3 the same number. They're written in binary, written in decimal, written in hex. The easiest way for you to do this is on the scratch paper, practicing, and probably also the one if you go physically and take the exam. You'll be able to use a scratch piece of paper, a white erase board, or a white erase marker on a sheet, is to write this out. And you don't necessarily have to do the 2 to the 0, 2 to the first, 2 to the second, but that top level, working from right to left, we're starting with the base number to the 0 power. Then the next block is the base number to the first, base number to the second, base number cubed, base number to the fourth, on and on we go, okay? With binary, we stop at 2 to the 7th, okay? Because in the binary numbering system, there are only, there's 256 possible values in a block of 8 bits, okay, which is a byte. And those numbers will come into play. So we start, basically, but then you can see the number below is simply that number multiplied out. 2 to the 0 power is 1. Anything to the 0 power is 1. 2 to the first 2, 2 to the second 4, 2 cubed 8, 2 to the fourth 16. On we go. Look down at the 10. Base 10 numbering system is the same. 10 to the 0, value of 1. 10 to the first, value of 10. 10 to the second, value of 100. And on, and on we go. Now, I just stopped there because we don't need to go any further, but just so you can, you see that. So with the binary numbering system, what we're going to do is we are going to line up the numbers with these tables that we've created, and we can use that information to convert any number that we want into binary, or from binary into one of the other numbering systems. So I'm throwing this at this. That was just sort of an introduction. We're going to go into a demonstration because this is a whole lot easier to talk about when we're actually looking at it, changing values, and seeing how that worked. Okay, but here I just wanted to show you the similarity to the numbering systems And now we're going to work on understanding how I can get from one to the other. Because, and you may be already asking yourself, why do I care about this? IP addresses are binary numbers, but they're written in decimal format. So an IP address is written as, 192.168.224.100. That's the IP address. That's how it's written out. But in actuality, every one of those numbers can be expressed in binary. And on certain occasions, in order to be able to tell between different parts of the address, we actually have to look at the binary. Okay. Now it's rare, but it's realistic, and it's just something that we are going to need to know, and it's something that they'll definitely test on for certification. So it is relevant. Not something you have to see and utilize every day, but it is a relevant topic. All right, in this demonstration, we're going to take a look at the numbering systems, and we're going to discuss how you go about converting from one numbering system to the next. Now, in our last slide, we showed that all the numbering systems are the same, except they use a different base. Okay, binary is base 2, decimal is base 10, and hexadecimal is base of 16. Okay, with binary, the other thing you have to remember is typically we're dealing with 8-bit numbers. When we get into real life situations, we're always dealing with at least 8-bit numbers, 32-bit IP addresses, so it's 4 combined 8-bit numbers, that kind of thing. In just general conversions, you may actually be asked to convert something and they only show you 4 or 5-bit, so we'll get to that. The biggest key here is coming up with your table specifically for binary of 18, 24, 32, 16, 8, 4, 2, 1. You can do that whatever way you want. You can start at the left with 128 and just divide by 2 each time. You can start at the right at 1 and just double the number each time. That doesn't really matter, okay? We know from the previous graphic that these come from the fact that 1 is 2, the base number, to the 0 power. 2 is the base number to the first. 4, base number to the second. Base number cubed, base number to the 4th power, right? Okay, so that's how we're not just coming up with those values. When we go at decimal, and this is going to be a little bit difficult to line up, but when we go decimal, well, what's 10 to the 0 power? Well, it's still 1. Okay, what's 10 to the first? That's 10. What's 10 to the second? That's 100. Okay. So we still have those values, and then we've got 1,000, 10 to the third. And I won't go any further from that here. Okay, but you still have those same kind of numbers, and the same thing goes for the base 16 hexadecimal numbering system. Starts at 1, goes to 16, immediately goes to 256, and then immediately goes to, I think, 4096. Point is, the numbering systems all work the same. All right, let's say number like 224. Okay, so there's 224. Now, you and I may have done this back in earlier math days where we had to write this out in exponent form. Well, if you had to write it out in exponent form, then you would take each of these and treat them as a different number. And so basically you would say, okay, there's 4 ones. There are 2 tens, okay, and then there are 2 100s, right? And if you were to write it out, I remember writing like this: 2 times 100 plus 2 times 10 plus 2 times 4, okay? So we would write it out like that, and we know that, okay, that's 200. That's 200 plus 20 plus 4. Okay, so 200 plus 20 plus 4. That gives me 224, right? And I remember doing this at school going, why in the world are we doing this? It's just, there's multiple reasons probably why they have you do it. But the numbering systems do all work this particular way. It's just when we see decimal 24, we know, hey, that's $24. Well, that's 24, yo-yos or whatever it is that we happen to be talking about. We don't need to think in terms of the placement, but the fact remains it works exactly the same way. The difference and what throws us off, particularly with binary, is that there are only 2 possible values because of the base 2 numbering system. So you can't have 0 through 9. You don't have all of these different options. Let's just cut this out of here. Okay. So if I wanted 224 in binary, how would I do it? Well, I would lay this out. Okay. If a couple of tricks, if the number that you see in decimal is any of these numbers, okay, well, then that answers the question for you. All right. They probably won't do that because that answers the question for you. Is 224 any one of these numbers? The answer is no. If it was, like if I had 32, then I'd look up here and say, oh, yeah, that matches one of these. Well, then that just means every other one of these is 0. Okay, and then there's a 1 on the 32-bit. That would be, so if you see the number, then you have to say, okay, there's a 1 in that slot and a 0 in every other slot. So all conversions start with that. Secondly, how big is the number? Okay, because like if it's 15, then you know that you can't have 128, 64, 32, 16. It can't be. That's not possible. Because if there's, in order to convert, we're going to take that binary number, or we're going to say we're either counting this value or we're not. Okay, so you ask yourself the question, can 128 come out of 224? Well, yes, it can. Okay, minus 128, and that's going to equal what? 64? No, that's going to equal 96. Okay, so you can take 128 out. So we're going to count that value. Can you take 64 out of 96? Yes, you can. We're going to count that value. If you subtract 64 from here, you're going to get 32. All right, 32 matches a number that's up there, so we know it's a 1 there, and that means that the rest of these are set to 0 in an 8-bit number. So 224 is 111-00000 in binary. Okay. Convert that back, you can. You will have you do have, I should say, a calculator. That this calculator will not be available to you on the exam. In Windows 10, you got to switch it to programmer mode. And you might do this just to check yourself, okay? And it shows you right away the hexadecimal and the binary. Okay, there's an octal numbering system as well, but that's an odd one that we don't use in networking. Okay, so you can take it and you can convert from binary to decimal or back and forth just by plugging in those numbers. I'm not saying to use this to do the conversion. I'm saying to use this to do just a check for yourself, okay? Because they will potentially ask you to do that. Now, what if they're asking you to convert binary into decimal? And what if they say like, okay, 00 like that? Here's a 5-bit number. Key thing here. There are no 5-bit numbers. So you always, at this point, you will have to start over at the right. Okay, you cannot start over at the left. In fact, if it makes it easier for you, assume everything's an 8-bit number and add the preceding zeros. Okay, so if they only show you a 5-bit number, that means there are 3 zeros in front of that number. And that plays a big role when we get here, right? There's a big difference between 1s in those 3 spots, which is equal to 224, and zeros, and the 1s starting here. Okay, so basically, though, this is all you need is your table, and then you just go, and if there's a 1, you count that value. So in this case, we're only counting the 16, the 8, and the 1 bit. So that's 16 plus 8 plus 1. And you figure out what that is, 25. So that's, this number, 11001, is equal to 25. And so just, keep that in mind. Converting from decimal back to binary, look and make sure that doesn't match any of the automatic values. Or some other times it'll be like obvious, right? It might say 48. And so oh, wait, I can add 32 and 16 to get 48. So that would be 1s and those values, zeros everywhere else. So sometimes there are some obvious ones, like 255 would be an obvious one. That's all 1s. 0 is obviously an obvious one. But even things like 252, 254, you might think, wait a minute, okay, that's obviously only not counting the 1 bit or the 1 bit and the 2 bit. So save yourself some time there. And then if the number's high enough, always start as far left as you can go. when you are converting. Now, the hex numbering system is a bit different just because it's got values 0 through 15, and we have to be able to represent something with a single digit. Okay, I can't throw 1 5 at you and expect you to know whether that's 15 ones or 116 and other ones. Here, I'm just going to do this. The one, sorry. Here's the hexadecimal numbering system. We're going to go 1, we're going to go 16, and we're going to go 256. Okay, I'm just going to deal with 3 there. Most hex numbers you see will be less than 3 digits. Often they're just 2. Sometimes they might even just be 1. Okay, what I'm saying is if I threw you, because those values are like that, because there are 15 possible values, 0 through 15, we have to use letters. Because if I were to throw up 1 5, you would have no way of knowing whether that was 1 16 value and 5 1 values, or is it 15 1 values? Well, there's a difference, right? The first one would be technically 21. This one would be 15. So we have to be able to represent everything in a single digit. And so with hex, at 10, we're going to switch to letters. So 10A, 11B, 12C, 13D, 14E, and 15F. Okay? So don't get thrown. That's all that means. So if you see a number like A0, well, like that. I mean, if you're converting it into decimal, which is actually kind of odd to be doing, then it's going to be whatever, 10 times 16. That's technically going to be 160. Okay, there's 0 in the zeros. What often happens is you get converting from decimal to binary hexadecimal to binary or binary to hexadecimal. Now, this may sound complicated, but in hex, in binary, every 4 digits can be represented as a single digit of hex. Okay? So if you had, the key here is just knowing that you're always dealing with this 8421, the right-hand side of that table. You're never dealing with the other ones. But if you had a number like that in binary, that's 9. Okay? That's 1001 in binary, 9 in decimal. What would it be in hexadecimal? It would actually just still be 9 in this case. Okay, so that's going to be 9. What happens if you get into another or a higher bracket? Well, 1110, for instance, 8 plus 4 plus 2. Okay, that's 14. So that's going to be your E value. Okay, but it's still all in the first. Place. Okay, what happens if you have a full 8-bit number? How would you do this? Let's see. Let's go back here. 1. Oops. Okay, let's use that number for instance. You have to convert this into hexadecimal values. Basically, you want to do it 4 bits at a time. Okay, so and I'll show you how this works out. So you want to do the first 4 bits. Okay, that's 2. All right, so that's going to mean that it is actually 2. And then you want to do the second 4 bits. But here's the confusing part. Forget these values. We have to treat every one of these, I had just gotten done saying it, as if it was a 4-bit number. We're always dealing with these. It'll screw it all up. Trust me, you'll see what I mean. So actually take, and we want to kind of cut that, and I'm going to put it over here. Okay. So the 8, the 4, the 2, the 1. Well, that's obviously 15, right? So it's F2. Now, just to make sure, let's check ourselves, because you might be thinking, well, how did that work? You're moving bits over. No. We're just really treating every number. For binary to hex conversion, we're just treating every number as if it is a 4-bit number. Okay, we're not moving anything. That's just more for example. So I mean, let's check the work. What was the binary number? So I'll click on binary, and we'll go. Let's see. It was 11110010. Okay. In decimal, that's 242, and look what it says in hex, F2. Okay. So just, I mean, and that maybe you're going to need this for 1-2 questions tops on this exam, but it is there. It is an important skill. It does come in handy when dealing with definitely IPv4 and IPv6 addresses in terms of hex. So it is something that's important. Use the calculator, but also try to use the calculator just to check yourself. So for the key for hex to binary conversion is treat, or vice versa, is treat each hex digit as a 4-bit binary number. Because the 4-bit binary number has the values of 0 through 15. And hex accounts for values of 0 through 15. So you have to keep each grouping, no matter how long the address is or how long the number is. You got to divide the groupings up into groups of 4. All right, so there you have it, the binary numbering system, the decimal numbering system, the hex numbering system. Probably not what you may have been expecting here this early on, but again, these are fundamental things that play out in the rest of networking and certainly in the certification exam. Now, there are a few different ways communication can occur over the network. And this is just kind of a generalization. Unicast is 1-to-1. Okay, so unicasting is a connection from a client to a server. Okay, multicast would be 1-to-many, and broadcast is 1-to-all. And I'm looking at our graphic there, and I see. You know what I didn't notice, and I'm glad that came up, because you might be looking at that graphic going, "Aren't those the same thing?" The top graphic is unicasting. It's the server sending multiple packets. They're still going through a router to individual clients, but it's multiple packages. Okay, so I have 6 clients I need to communicate with. Unicast will send a separate package to each of those individual clients. Multicasting will send a single package to a group of clients. Okay, and basically that sounds just like it's still pretty similar, but it's one package. And then there's a group protocol that allows clients to subscribe to that. Okay, any sort of conferencing is probably the best visual representation for us, or example for us of using multicast. Broadcast is going to be one to everybody. That's like shouting. So it's, instead of just sending it to somebody, I want everybody to hear me, so I'm going to blast packets all throughout the network. Okay? Obviously, that can be a problem because of network congestion. If you've got machines that are just shouting out, they're eating up network bandwidth. We'll, of course, get into that later. So broadcast has been minimized over the years, and it's not used as often, but there are still certain times where it is going to be required. So unicast 1-to-1, multicast 1-to-many, and broadcast 1-to-all. Some other communication concepts that we need to have, and these graphics get a little deeper than we need to go right now. Okay, so I have them on here because they represent encapsulation, de-encapsulation, but let's not get bogged down in the details of two systems communicating with one another, other than to say the graphic on the right, on computer A, it is encapsulating all of its data into network packages to send to computer B, and on computer B, it will de-encapsulate. So encapsulate is to package. De-encapsulate is to remove the package. All right. Now, obviously, it gets more detailed in there. What is all because what the other parts of the graphic are referring to are the types of data that are in the package. And there are multiple types of data. But as I said, I'm not going to jump into that quite yet, but it's just a process of packaging things up. Let me give you, for instance, I'm on a web browser and I'm going to a website. There are so many things that have to happen when I type in the name of that website. And this happens so fast that it's really hard for us to fathom every one of these things is happening every time. And the answer is yes. But we have to remember that we're dealing with computers that can do things in extremely fast periods of time. Most of us are looking at our computer wanting it to speed up. But if we could actually wrap our minds around how much is going on every given millisecond, then we'd probably give it a little bit more of a break. So again, simply put, encapsulation is packaging. And within the package, we have to have all the data that is going to be needed by the destination system. Okay, and so there's going to be application layer data from the web browser. There's going to be TCP data that's going to identify the application. There's going to be IP data, which is how we're going to route and possibly security. And then there's going to be just physical information. I mean, ultimately, this has to be put into an Ethernet frame or a wireless frame. And a frame is that structure that's required by the particular network you're connected to so that I can transmit a package from source to destination. Nobody else on the network cares about the data that's inside the package except for the source system and the destination system. So encapsulation and de-encapsulation are just that process. In this next topic, we'll be looking at network models and topologies. Models is sort of the organization and the layout, but sometimes logical layout. Topologies is a term that typically gets used in terms of the physical layout of the network. So networking model used to describe the type of network as it relates to methods of administration, types of systems. Again, the management, the organization is kind of how I summarize those two things. And we have basically two options, peer-to-peer or client-server. Okay, those are the network models. In a peer-to-peer, also known as a work group, we have a bunch of individual machines that are connected to the same network, but essentially handle their own security. All right, that's the easiest way to think about it because the security and the administration is decentralized. Every computer system, at least running the Windows operating system, Linux as well, has a local database of user accounts. You have to have a user account on that system to sit down and log into that system. You'd also need a user account on a system if you wanted to try to connect to it remotely, like to a shared folder or a shared drive, shared printer, those kinds of things. I have to make myself known to that other system because each of these user databases are local within that client operating system. And so, yeah, they're simple and easy to set up. Basically, just connect to the same network and join the same work group. Windows 7, Windows 8 had the term home group, which was kind of the same thing, but even further tried to simplify it in terms of sharing and access. And I believe that option is still there for Windows 10 and 11, just only used on very small home type network. So very easy to set up. Any types of data devices can be used to share data, but the key disadvantage of this is going to be that decentralization. So once you get into business environments where we have 5, 10, 20, 50, 100 computers, a few dozen servers or something, then obviously we need centralization. We have to be able to manage those. We don't want to have to create accounts on multiple machines. We don't want to have to deploy applications individually across multiple machines. With a client-server domain type environment, you have that level of centralization. Number one, it acts as a group of systems. So when you log in, when you authenticate, you're actually authenticating to a server. And the server can authenticate multiple clients using a single user account. A user account for each person, a computer account for each computer. We can accurately represent what's on the network. And not only can we do that, but we can then push out and actually control or administer those machines. If I'm an admin on the server, for instance, a domain admin, I have administrative privileges automatically on any machine in the domain. I have higher level privileges across multiple systems. So we can do that administration from a centralized point of view do. Certainly client-server networks are larger, therefore they require additional planning. They typically would have ongoing administration needs. Now, sometimes you can have end users that have kind of elevated their knowledge, their tech savvy per se, and they can handle things like adding user accounts and whatnot once it's already up and running. But troubleshooting, we're going to need an IT department. New setups that interact with our domain, we're going to need an IT department. And if we don't have one as a company, then we would outsource it, and that's where your consultants, your MSPs, and things come in, right? But it's going to require administration. It requires a higher level of knowledge, an understanding of directory services, of network protocols, of various network devices, etc. Sharing is done in the client-server model, just like peer-to-peer, but it's typically done by dedicated servers. So usually we have we have folders that are shared on the servers that multiple clients are connecting to. That's where the majority of the company data is stored. That has a lot of advantages, such as having one place to back up, just as a for instance. So let's break these down a little bit more. It's a key distinction. So in a peer-to-peer, security is handled at each workstation. And so it requires that you have accounts on each device, or it requires that you use shared accounts. Now, if you use shared accounts, you're talking about multiple people logging in as the same person. From a security perspective, not a great idea. However, creating accounts on every computer in a workgroup scenario is tedious. What if I have 5, 6 machines and somebody legitimately has to access data on other systems? Okay, well that's tedious. That typically doesn't get done. That's where the home group came in Windows 7 and beyond, because it would handle that authentication for you. And so it would allow you to say, here's what I want to share with others in my home group without actually having to create the account. So it was trying to simplify it. But security is still limited. I don't have the same policies and controls as I would have in a Windows network, any larger corporate environment. All of your configuration management, that is adding, removing programs, modifying control panel, PC settings, updating the registry, Windows updates, all of that's local. All of that's decentralized. So practically speaking, a work group is 10 systems or less. Client-server domain, security is handled on machines known as domain controllers. The most common of this, predominant, it's got to be 99%, it seems like, from my perspective, is going to be Windows machines. Handling the directory services, handling the user accounts. And so, because security is handled by those domain controllers, you have single sign-on. You have SSO. That means I can log into my computer, but I'm technically logging into this group of computers, and the username and password is going to be the same one that I use for any of them. Therefore, don't ask me again. That's single sign-on, right? So I sign in once, and I don't have to sign in again. And there are variants of that where you might be asked to sign in again, but you just use the same username and password. But true full-on SSO does occur within an Active Directory domain environment. That's a Windows domain environment, and and you have single sign-on. You're not going to be asked again. So as security is also maximized just because of centralized configuration management. I can patch systems much better. I can remove unwanted software. I can ensure security controls are in place. Firewalls are turned on. I can do all that with a click of a button in a domain, click of a mouse. In a peer-to-peer work group, that would require an extensible amount of effort. So this is scalable up to enterprise level environments. Truly, Active Directory environments, domain controllers can host hundreds of thousands of objects, potentially. All right. So it does work for small networks, even 5 to 10. We could get a lot of advantages out of using a domain or something of that concept, maybe cloud-based domains. With some level of management is always going to be ideal. Now, the network topology relates to its actual layout, either logically or physically. The logical topology defines how data actually flows on the network, whereas the physical topology defines the actual structure, the actual layout. We're going to, unless otherwise mentioned, I should say, you should always assume they're talking physical topology. That is the most common way that the term topology is going to be used. What's the physical layout? Multiple topologies exist. They're going to vary in use. This is somewhat of a historical thing. We've more standardized these days, eliminated a couple of these, but we still have to remember them. Bus, star, ring, mesh, with a couple different variants on mesh. So let's start with the bus topology. The bus topology is just a single line of cable. That makes it simple to configure and inexpensive because you don't have to pay for a lot of cables, but that brings some obvious disadvantages. Okay, if we've got a single line of cable that is connecting multiple computers, what happens if that cable breaks? Obviously, that eliminates everything. We can see in the graphic terminators on the end. What happens if one of those is faulty? Well, again, no communication across the network. So prone to failures, and typically failures involve everybody. This is historic. A physical bus is historical in terms of coaxial cable and the original Ethernet standard, which we'll get into. So it was used for that, is certainly no longer used, but there may still be times where you run into a physical bus. That's any single physical connection between one system and another. That's going to be, for that portion of the network, a physical bus. So where is it used in modern networks? Well, it's typically used for backbones. So a physical bus might connect multiple switches or routers, in an enterprise environment. There may be times where you have a single cable, therefore you have a physical bus. But in the old traditional sense, legacy network sense, this is not something you're going to see. Physical star, on the other hand, is what we have now standardized on, largely because of the Ethernet standard, which is what everybody uses. The Ethernet standard defines essentially a physical star topology, which is a single line of cable from each individual node to a central device, a central connectivity device. Therefore, failures are handled better. Why? Because it only affects one system. It does require that central connectivity device. That's going to be a switch or a hub. The term router could be used here. If a term router is being used, it's likely this centralized device has multiple functions. Okay, so in the true sense of the word router, well, that's its only function, would not be the central component in a star topology. A switch is by far the most common this day and age as that central device. So individual cables for each node, and as we said, this is used on most modern networks, especially when we get to the point of connecting client devices, because at that point we wouldn't want the failure of a single device to affect the rest of the network. Ring is another one. This is a physical ring, is very similar to a bus topology. The nodes are connected in a circular fashion. It's got the same disadvantages. It's prone to failures, nodes being disconnected. Nodes have to actually be online to pass the packet. And so some more modern implementations would implement a secondary ring like the FDDI, Fiber Distributed Data Interface, which is more of a WAN technology using fiber optics, but that secondary ring would add redundancy. Okay, this is used in specific scenarios. It is highly unlikely that you will ever see this again. This takes us back quite a good number of years, but it's still just kind of a traditional topology that we've seen. So not saying it doesn't exist anywhere. There are going to be places, but it's highly unlikely that you'll encounter this in the real world. Then we get to mesh. The whole concept of mesh is that you will have multiple connection points between each node. Obviously, this goes to the other end of the spectrum in comparison with the bus and the ring models, which only have a single line of cable. Now we're talking about multiple connections between nodes. Now, it's I'll jump down to the two types because this is fairly straightforward. Either each node has a connection to every other node and is a full mesh, or each node has connections to at least two other nodes and is a partial mesh. Okay, so the graphic on the top, if we just look at that bottom left computer, we see it has connections to each of the four other computers, right? Whereas in the bottom graphic, take the router and center bottom, it's only got two connections. but there are 4 other nodes. All right, so that's a partial mesh. So in any case, it's going to be expensive. The cost certainly varying on the number of connected nodes, but in any case, it's also going to be fault tolerant. That means we can sustain the failure of a particular connection link and still remain connected, still be able to communicate. And that is the very reason why this is done. And so it requires connections and media between some or all of the nodes, and it requires separate connection paths if you're going to have redundancy. So we would see these in potentially in data centers. You could potentially see a mesh topology between routers to form a wide area network for a larger organization. You know, that's where you would see this. Virtualization clusters would be another one. Often we have multiple hosts, and they may have multiple physical connections to a storage area network, the same storage area network. So that's a form of a mesh topology. So sometimes it's access to storage over the network. Sometimes it's access to other systems. Sometimes it's devices that are routing and switching packets. Those can all be lined up in a physical mesh. Now, along with the physical topology comes the logical topology, and the logical topology is the way the data flows on the network. And quite honestly, unless I'm actually wiring networks, I don't really spend much of my day thinking about network topologies. And it's not that I have to think about logical topologies either. It's just the logical topologies have actually a bit more to do with day-to-day life and a bit more influence in our understanding of how networking works, okay? Because I can get the idea, okay, I just run a cable from here to the switch and I'm connected, and anybody else connected to that switch in that star configuration is then connected to the same network. And in the case of wireless, if we all connect to the same wireless network, then there's a sense in which we are connected because we're on the same physical network. One just happens to use radio waves. But beyond that, we don't necessarily care. Beyond that physical connection, media matching, those things, we don't necessarily care. It's the way the data flows that has more of an influence on some of the other decisions that we make. So in a bus logical topology, all nodes receive data all at the same time. There's one signal per line in a bus topology. The logical. And so that suffers from collisions, that suffers from slower throughput. Basically, it's when I'm trying to talk, am I able to talk just with just with one other system, or do I have to involve everybody in the conversation? Well, you can see if I have to involve everybody in the conversation, that means while I'm talking, nobody else can talk. This really is how networking is functioning. You know, if I'm speaking, you can't speak. If you do, there's going to be a collision. And actually, both packets are generally destroyed, and both systems then have to sit back and wait and try to send again. The more of those that you have, the slower the network is going to go. But that's the logical bus topology. And if you're waiting for me to say, well, guess what? We don't really use this. But we do, because Ethernet is a physical star logical bus. Ethernet, traditionally and still to this day, suffers from this. But nowadays, we have ways to mitigate that. This used to be a massive problem 20 years ago, but now we have ways to mitigate that, and we'll get into those. So logical bus, one person speaks, everybody hears. Only one person can speak at a time. If two people speak at the same time, then you have a collision and you have to wait. The ring has a deterministic factor. The logical ring, which is used in token ring networks and FIDI networks, basically if they use a physical ring, they use a logical ring, but it's a very small subset of networks. But in this case, each node receives data from an upstream neighbor and passes it to a downstream neighbor. So it flows in a logical ring. Sometimes more modern token ring, which is still 15, 20 years ago, would use a physical star. So they'd use the logical ring topology, but they would use a physical star layout. So it would maintain that communication. So this is it looks like the same problem as the bus in that basically only one person can talk at the same time. But the elimination of collisions through that deterministic factor means that you're actually not going to have any collisions. And collisions are a big part of the slowdown. Networks can process tons and tons of data, at the same time or going, together. In a chronological order, but it can do so very, very quickly, so where you and I wouldn't even notice. Collisions are actually what slow things down. The deterministic deterministic method used in a logical ring is the best way. And it is a virtual like token. Like, just think of an empty package. And basically when the package gets to me, if it's empty, I can choose to take it off the network, place data in it, put it back on the network. But that can happen, of course, hundreds, thousands of times in a given period. Seconds, really. We're talking computer systems, okay? So, but it is still, you have to have the token, therefore there can't be any collisions. Star is all nodes are wired in the same bus cable, but a central device known as a multiplexer tries to determine how to transmit data. We don't see a lot of logical stars, all right? You're going to see more, pretty much this day and age, it's going to be a logical bus type of topology. Now, there are wireless topologies as well. These aren't physical layouts per se. It's more of a logical thing. You still have a physical component. I still have a physical NIC. This NIC just transmits over antennas using radio frequencies. And so, I mean, if that's the case, then that's the physical part of this connection. I can't touch it, but it's still the physical part. Mesh means the same in wireless topologies as it does in wired. And with wireless, this would primarily be used for access points. You would think any systems that had to be communicating with one another. Ad hoc is a one-to-one type of wireless relationship that can be easily initiated between two client devices. That's typically where ad hoc type connections would exist. You don't see ad hoc being used to provide internet access. It has in the past through things like internet connection sharing and the Windows operating system, but those really were flaky, didn't work well, opened you up to things. Ad hoc connections are always something to look for, and you don't want to connect to them if you're trying to get a hotspot out to the internet. But you'll find, you go to Starbucks, you go to an airport, you're going to see ad hoc connections advertising themselves to try to give you internet. Those are a general bad idea. Vast majority of the time when we're connected to wireless, we're connected to infrastructure mode. And that means I'm connecting through a wireless access point. The wireless access point, or WAP, is then connected to a wired network, which is connected to the internet. Okay, that's your hotspot, and that's all the only term I have to say for us to know, okay, yeah, that's the vast majority of Wi-Fi, is there's an access point. It's not a one-to-one connection between computer A and computer B. Computer A is connected to the access point. Computer B is connected to the same access point. That's the infrastructure wireless topology. In this next topic, we're going to look at network components and services. Now, this is just going to be kind of a high-level overview. We are in the network fundamentals chapter, just of what are some of these other things beyond physical devices, wires, cables, wireless, etc. What are some of the components and services that we would see on the modern network? So these are functions that are provided by the network, and we just typically call them services. And it's a general term for a particular concept. Right? Earlier we said computers are connected together in a network in order to access resources. Well, it's the services that provide access, the services that are run on a server that provide that access. So file services, you can probably guess, right? What is file services? It's access to a network shared folder. It's access to a shared folder that's in the cloud. Okay, regardless of where the shared folder is, if it's not on my system, it's being offered through some form of file services. It is, in the Windows Server operating system, it's a simple file and printer sharing type of service, and the Windows client as well. Print services are access to printers. Print services can run on the physical print devices themselves, and often do these days. Those devices would be multifunction devices. They'd have a web page that would allow you to configure, scan to email, scan to folder, all the various other settings that can be set up, security settings and whatnot. So they are their own print server. But in some cases, especially historically speaking, we've had actual Windows servers, operating systems that function as a print server, and all they're doing is sharing out logical printers that point at physical devices and then each individual client computer is printing through the server. And that has the benefit of centralizing log files and centralizing queues and just having better print management. Okay, so that's print services. Authentication services. Authentication is all about who you are and the system verifying that you are who you say you are, usually through the combination of a username and a password. All right, there are additional authentication options that are available, but that's in general what authentication services are all about, is just, hey, I have to be able to successfully identify you. So there are authentication services that exist on individual Windows machines, right? You can tell it to log in for you, but you have to log in as an account to Windows. Same thing on Linux, same thing on Macintosh. You have to log in as an account, but there are also network services like Active Directory in a Windows domain environment that provide authentication. Centralized authentication, as we were talking about before. Name resolution services are resolving user-friendly names to numerical addresses, typically IP addresses. We also have name resolution for MAC addresses, and we'll discuss those different addresses that exist for a NIC. But name resolution is key because you and I, we don't think in terms of numbers. I go to google.com, I don't go to 201.114. I'm not going to remember the IP addresses of these places. I'm probably not even going to remember the IP addresses of all our internal servers. I'd rather just call one mail or DC or FS for file server. I'd rather use a user-friendly name. It's name resolution services that are helping to translate that and translate it so that the computer knows what we're talking about. We also have IP address, or you could just say address assignment services like DHCP that automatically assign IP addresses to clients. We're going to have an IP address to be able to communicate on a TCP/IP network. We'll talk about that in great detail later. That is the logical configuration of the protocol, is having a unique IP address. Well, clients have to get those IP addresses. Servers, printers, access point, they all have to get it. The easiest way to get it is dynamically by a network device that offers the service. Access services could be like remote access services. I mean, that's a fairly vague term. We could be talking about VPN services on a server operating system. We could be talking about remote desktop services. That's probably a more common one, running on a Windows operating system or through like the Citrix application and other web application options. Communication services are just communication platforms. So you could think instant messaging and voice. Those would be communication services, but probably your most common one is going to be email, right? Electronic mail communication. That is going to take place on a daily basis. So there are services that happen on the back end to be able to facilitate that. And then there are all manner of internet services. That's about as broad as it gets. Services provided by the internet, services provided by cloud-based providers, that may fall loosely into some of these other categories. But as I said, these are just kind of generalizations, but knowledge of these is very critical in becoming an efficient networking professional, because it allows us to resolve issues quickly and completely. Understanding the different pieces is really, really going to be key. That's basically what that statement is saying. If I'm attacking a problem from the perspective of the client and I don't understand the components that reside on the server that could also affect this, I'm going to be limited in what I can do. Right? My knowledge of all of the pieces of the puzzle are going to help me to be able to put it together, to figure out what's missing. What component, where does the problem reside, and what component can we fix it to resolve that issue? There are lots of other management services. These are just kind of, again, some general terms. Traffic monitoring is the ability to view network traffic and see communications that are happening. Traffic control would be the general ability to restrict. Okay, so both traffic monitoring and traffic control are largely going to happen on security types of devices like firewalls, right? And we've got security functions within switches and routers as well to do the same thing. Control the traffic, view the traffic, but also control what can and cannot go through. So that's typically at a network device level, could be at the system level as well. Load balancing is just the concept of splitting the load between two systems that do the same thing. Think two web servers, two mail servers, both have access to the same mailbox. Well, I'm going to do load balancing. I don't want every request going to one server if I have 4 web servers that can do the exact same thing. Right? So we load balance the request between them. Load balancing can be done virtually through software. It can also be done with physical devices. Asset management and license tracking, these are usually network services that are responsible for just knowing all of the components on the network and keeping track of it. All right. Something like System Center Configuration Manager in the Microsoft world, SCCM, formerly known back in 2003 days as SMS. 2003, 2006, I believe. Anyway, it's about management of devices, pushing apps, deploying operating systems, things like that. But it's also about having a track, an inventory of all of those devices. Tracking for software licenses and whatnot, because it allows you better capabilities to do change management. Change management just in general is just a kind of a formal process that we do to implement change in the environment. Security auditing would be another monitoring type of service that exists, where I'm basically tracking events like sign-ins to a domain controller, sign-ins to the Azure AD cloud or a particular other cloud-based application like Sage's accounting software or whatever it happens to be, right? There's tons of different software that's out there. Security auditing is just monitoring security related events. Software distribution is all about pushing apps. Once again, that can be done in an on-premises environment. That can be done in a cloud-based environment. We're going to be talking a lot more about cloud-based as we go through, because there's a lot of that going on today. Address management, typically that's just the management of those IP addresses, backup and restoration of data. These can all be centralized services that are available on the network that allow the network to function in an efficient way. In this next topic, we're going to just take a look at some of the network standards that are out there and the ones that we're most likely going to encounter and need to know about. So first off, what is a standard? Well, it's a set of specifications, guidelines, other characteristics that are applied to networking components in order to provide interoperability and consistency. See, standardization in networking has been has brought on a massive wave of development. We have come so far since, let's just even say, the mid to late 90s in terms of the internet's availability, what's on the internet, what's available in the cloud, virtualization, etc. I mean, we're all talking about 20 years, and that's basically since the complete standardization of things. TCP/IP as the standard protocol of the internet, HTTP as the standard application layer protocol to communicate between browsers, but certainly other application protocols. In terms of web pages, HTML code. Okay, they're like the basics, and then everything just kind of grows from that. TCP/IP, though, is the underlying glue that holds everything together, and TCP/IP is simply a protocol that operates on what is of another very common standard, and that's the Ethernet standard. So you think of a standard as just, okay, this is a list of things. We've got multiple vendors that are going to be producing devices, applications, operating systems, you name it. Could be any number of these. We need to provide standards. So all they have to do is make their particular components work with these existing standards that are out there. And if you can work with TCP/IP, if you can work with HTTP, then guess what? You can communicate on the internet. That's it. But it goes well beyond that. I mean, that's a great simplification. But the point is the standard provides us with this kind of modular structure where we can just plug into things that are already there. And I don't have to worry about every aspect of an application and its communication with the network, just basically how it gets connected to the network and what protocols it's capable of using. The standards will apply to virtually all parts of a particular technology. So there's standards for different types of cables. There are standards that define a particular type of connector, a particular length of cabling, how you actually transmit and receive data across those mediums, the types of signals and whatnot. Those are all defined in standards. So we use standards because if we just let multiple vendors kind of go willy-nilly, well, that's going to result in inconsistencies at best, but even worse, incompatibilities. No, I can't actually communicate with you. Why? Because you have a Dell computer and I have a Lenovo? No, obviously that would make no sense at all. It doesn't even make sense to our brains these days in terms of browsers. What do you mean your application only works in Internet Explorer? That can't be true. But there are some old legacy applications that have never been upgraded. They only work on Internet Explorer. You have to use Internet Explorer. As soon as you try to use Edge or Chrome, it fails. You know, that's an example of what not to do. That's an example of incompatibilities, because we all just kind of assume these days it should work. Right? Your website should work on my laptop. Your website should work on my phone. It should work on just about any device that I touch that's connected to a network. Right? That's the way that we think. Well, standards help you to achieve that. Without standards, manufacturers could also make any claims about their devices. So standards define the actual, minimum acceptable levels of performance. The standards still provide the room to enhance capabilities within a particular framework. So you'll see lots of variants. I mean, the original Ethernet came out in the 80s. Okay, so we're obviously not using that original standard, and there are going to be enhancements along the way. So there are a lot of standards organizations, and the first thing I'm going to say about this is don't worry about it a great deal. Some of these are definitely not on the exam. I just kind of threw them in there. ISO, the International Organization for Standardization, works on standards for a lot of different security protocols, web protocols, things like that. IEEE, Institute for Electrical and Electronics Engineers, that's the one that I'm surprised they took off, but it is not actually in the acronym list for the exam. But IEEE creates network standards, and so Ethernet, token ring, wireless, Bluetooth, the WAN technologies, those are all developed and standardized by the IEEE. ANSI is the American National Standards Institute, produces a number of coding types of standards. TIA, EIA, that's one that we would actually see just because that's the standard that defines Ethernet cabling. That's the organization, I should say. But the standard itself is called EIA, TIA. That's what it's referred to as. IETF is Internet Engineering Task Force. That's basically all about web applications. Essentially, you can go look up these if you'd like, and you can certainly get more information that way. These are not, this is just kind of outside the scope of the test. But as we're talking about standards, there are centralized organizations that very job is to sign off on the various standards that are out there. So the 802.x standards, which is IEEE, this does directly apply to computer networking. These are divided into subcategories to address different requirements. The original was 802. That's no longer being used. 802.2 developed to address the need for a MAC sublayer, addressing in switches, and it also specifies frame rates and transmission speeds. That's also very early on. 802.3, the original, this is what people point to. In fact, Ethernet is still called 802.3 to this day, although it'll always be 802.3A, B, AX. It'll be something else at the end, some variant of it, but that is the Ethernet standard. 802.5 is token ring. 802.11, that's definitely one that we will see a number issued to address wireless LAN architectures. 802.15 is your Bluetooth, so your personal area networks. 802.16 is a type of wireless metropolitan area network. So those are just a few examples. Again, not really something you have to memorize, but these are the networking standards developed by the IEEE. Then you also have the 10-base standards. These we might see, it's really kind of odd. They removed IEEE, they removed the 802 numbers. You don't actually find those in the objectives, but they still have some of these 10-base standards. When, in reality, they're kind of all talking about the same thing. It's just a different way of referring to it. The 10 base, let's just say 10 base 2, for instance. Actually, we'll use 10 base T as our example. There's 3 parts to this. There is the number at the beginning, which is the number of megabits per second in the bandwidth. There's the word base, which is baseband, in contrast to broadband. Broadband, you can have multiple signals on the line at one time. Baseband, we can only have a single signal. Remember, we said Ethernet uses that logical topology. Everybody hears. That's because it's a baseband signal, only one signal on the wire. And then the letter or number would be a media specifier. What particular type of cabling do you use? Okay, and so the standard Ethernet originally, this is the first two are actually using coaxial cable, which we'll get into in the next chapter, but that's old. That'd be bus topology. We're not going to use that. Thin net versus thick net. Okay, 10 base 5, it goes 10 megabits per second, baseband signal. In that case, 5, it just means thick net, but you can also remember that means it goes 500 feet without the signal degrading. Okay, or I think it's meters. Sorry, 500 meters. 10 base T, it's a media specifier. The T just stands for twisted pair, so it's twisted pair cabling. So basically, again, they're just standards, but you kind of want to be able to look at it and tell something, right? So now we can move to fast Ethernet, which is still old. 100 base T, okay, that means the bandwidth is actually 100 megabits per second on a baseband channel using twisted pair cabling. Okay, 100 base FX, same thing, but using fiber optic cabling. And then there were a few different variants. There was TX, there was T4, and they meant different things. Okay, we see the TX. It wasn't 100 base TX. Sorry, I have a mistake in there. It was 1,000 base TX, which is gigabit Ethernet. Now we're at a gigabit per second. That's how fast we can be communicating on these networks. Remember, Ethernet is a LAN technology, local area network, so same geographic location. So now we can be going up to a gigasecond. And then, of course, there are a bunch of variants of that in terms of fiber optic. Okay, in terms of fiber optic, you've got 100 base FX, 100 base SX, 1,000 base LX versus SX. We'll get into some of those later, but it's just different styles of gigabit Ethernet. They're still all a gigabit, but the media specifier tells you the particular type of media. There are going to be different types of cables that we can use, mainly fiber or twisted pair. Now we have 10G Ethernet. That's 10 gigabit Ethernet. 10G base T requires Cat 6A for up to 100 meters over twisted pair. SRSW would be for fiber optics. EREW also fiber optics, but single mode. Okay, I'm not gonna bore you right now with the memorization of all of these, but this will be key to at least be able to recognize the speed and then the media that's being used when you are presented with a 10 base standard. Now, as I've said, Ethernet's the most popular form of LAN in use today, and it's largely replaced other technologies that were used in the past because it's easy to configure, it's easy to install, easy to administer, pretty low cost, very high speed. The physical star implementation cuts down, gives it some fault tolerance and whatnot. And Ethernet has evolved over the years, and it comes in a number of different types. And really the only difference between those types are the standard name, right? It's the speed that they operate with and the exact cables and corresponding connectors. Those latter two things we're going to get into the nitty-gritty in the next chapter. Here I want to just talk about some of the fundamentals, okay? Now, mind you, there's a ton in here. You don't need to necessarily know every single piece of this for the exam, so don't get too bogged down. But it's a good way of, you have all the information, okay? It breaks it down. So earlier I have used the term packet. That's the official term. I called it a package. The actual official term at the physical layer is a frame. And we did use that term earlier. I said, okay, you're packaging it up, encapsulating, and at the end, it gets put into a particular frame. Well, the frame is essentially just a container that gets it from source to destination. And on a particular network standard, like Ethernet, well, the standard itself is going to define the specifications for that package. The data has to be a certain size. Okay, the start of the package, the frame, has to identify who it's going to, among other things. The back end, the caboose of this package, is going to have to identify something else, and so that's what the standard is That's what the standard is showing. Okay, so the Ethernet frame is just a data packet that's been encoded at the data link layer. Talk about that later, for network transmission. I need to get it to its destination. All right. And so at that point, we don't necessarily need to get into every piece of this. Essentially, you have a Ethernet header. The Ethernet header is going to be everything from the preamble to the type. You have the data section, and then you have an Ethernet footer, which is that FCS, frame check sequence. That's what it stores. In the Ethernet header, it's going to predominantly be, the most important thing for us to know is that it identifies the source address of the packet and the destination address of the packet, okay? And so those are identified. That has to be in the very first part, the header of the frame, so that network devices, when they get it, they know very quickly, is this data for me or is this going to somebody else? Do I need to pass this on? Okay. And so that's what's happening. Destination address, source address. Those addresses are the actual MAC addresses, and that's how that's done. So we'll talk about that a bit more. Data is data. It's just defining. Okay, here's the data container. It's 46 bytes to a maximum, or MTU, maximum transmission unit, of 1500. That's the norm. Okay, and then the frame check sequence is used to do error checking. So the footer, the Ethernet footer, is going to have a way for the destination to make sure that they got exactly what was sent, that nothing was corrupted along the way, okay? That's the construction of an Ethernet frame. And as I said, you don't necessarily have to get into the nitty-gritty, but it's going to be key as we go forward to actually understand network communication. You're going to break it down into its different parts. And we can keep it simple here by saying in the header, it has the address information. The data section of the packet has the data, and the footer has the functionality to prove that the data that data integrity remain through the process of communicating that packet from one to another. So MAC addresses are key to this. Media access control is an address that's on your network interface card, and it's put there permanently by the manufacturer. Okay, it's a 48-bit address that is 48-bit hexadecimal address. It's represented as 6 pairs of hex numbers separated by hyphens or colons. Okay, typically it's colons. This is broken into 2 parts. The first 3 pairs are the manufacturer ID, and the last 3 pairs are an ID specific to that network interface. Okay, the actual acronym there is organizationally unique identifier. These can be modified due to flash ROM on newer NICs, but not typically something that we do. So the MAC address, when we talk about addresses, we're usually talking about IP addresses, and we'll be sure to make sure we know the difference. But the MAC addresses are typically put there by the manufacturer, and I never have to touch. I don't have to mess with MAC addresses. I don't really have to do anything with them, and so therefore it's uncommon to need to change them. Typically, that's that, and I deal with the IP address, and then there are protocols within TCP/IP that are going to resolve the MAC address from the IP address. Okay, as a user, I'm just using FS1, file server 1, please. Here's the IP address. Okay, who's using this IP address? What's your MAC? Here's the MAC address. All that stuff is behind the scenes, and I can communicate. If you do, mind you, need to change MAC addresses, you are actually doing what's called MAC spoofing. That can sometimes be necessary to get out through routers, but typically that's older router equipment these days. You generally don't need spoofing. Virtualization would be another place where we're kind of using IP spoofing in a sense, where we come up with virtual MAC addresses for individual systems. Another fundamental concept is the access method, the way that the computers actually get access to the network. So, I mean, clearly they're connected, so that's how they get access, but there has to be a way in which they get to communicate. Okay, so how do nodes gain access to the media? And they're loosely defined as deterministic and non-deterministic. And we've mentioned like token ring using a deterministic access method. That's what I meant. Ethernet uses a non-deterministic access method. So basically it's like all the nodes have equal access to the communication media. And that may seem like a good thing, but what it can result in is chaos. We think, well, isn't it better if anybody, how is it, I'm sorry, let me back up. Because for instance, we would say on token ring actually outperforms Ethernet. or can. And it's because one node can go at a time. There are never any collisions. Remember, I said without any collisions, then you don't have the major slowdown when it comes to networking. And so the thought is, well, how is that possible? Wouldn't it stand to reason if everybody can communicate at any time? Why if I have to wait for this package? Why would that be better? And it's because of the lack of collisions using that type of access method. So it would be chaos, I was going to say, because if you had a bunch of people like in a college class and everybody could just speak when they wanted to, it would be a little chaotic. We would like to have something that determines who can speak when. What we have is we're going to use Ethernet. The setup is easier. The media is cheaper. So we're going to continue to use that. Here's the access method that we use to try to mitigate some of those problems. So the method is CSMACD, and this is an acronym that you're expected to recognize. Carrier Sensing Multiple Access Collision Detection. Okay, so carrier sensing just means they all have equal access to the wire, so they can actually hear if something is being sent. That's baseband signal, remember? So one person sends, everybody can hear it. It may be directed to a particular person, excuse me, but every device is actually going to hear it. They all see it. So carrier sense, and multiple access. Multiple access, we have concurrent access to the media. Carrier sense, we're listening. I'm listening to make sure that nobody else is talking. If nobody else is talking, then I'm going to send. Now, if two nodes send at the exact same time, there will be a collision due to the baseband signal. And collision detection is if two or more systems transmit at once, they just repeat it. Okay, they wait. They back off using this back off algorithm. They send jamming signals basically to try to or everybody sends a jamming signal and then we back off for a particular period of time. That's not really configurable. So they're always, and then they just start the process over, try to send again. So the more collisions, the slower this thing's going to go because we have to sit and wait. So the key, and this is just kind of an overarching goal, our key in Ethernet is going to be to try to cut down on the amount of collisions. We can't talk about standards without talking about the OSI reference model. This did continue to be there in the Network Plus objectives. So the Open Systems Interconnection Reference Model is a framework that's used to describe networking communication. It's used by developers to create protocols and applications that interface with the network. It's not incredibly useful to you and I. For day-to-day administration, we don't really need this, but from a conceptual basis, it can be at least somewhat helpful. Again, just trying to get a bigger picture. Okay, I'm never going to be digging in and looking at a particular layer, but understanding where the problem is and the nature of the problem might direct me to an application layer protocol and what's providing that service versus networking issues because it's IPs and routing that appears to not be functioning, right? Or a firewall, which also be kind of at the network level or the transport layer. So having it as a conceptual model can be very useful for understanding what's going on, and that does assist in troubleshooting. Now, the OSI reference model consists of 7 layers. They are numbered in order from bottom to top. So the bottom is layer 1, the top is layer 7. They also have names. Each layer is doing something in particular and adding certain types of information to a packet. And then network devices also operate at a specific layer. An easy way to remember this, and again, this is on the objectives, an easy way to remember it is from bottom to top using sort of a mnemonic. So using the first letter, PDNTSPA. Please do not throw sausage pizza away. And that's one that is as old as I am in terms of IT and networking. I heard that when I first got into it as well. So anyway, please do not throw sausage pizza away from the bottom to the top. Sounds kind of silly, but the sillier it is, sometimes the easier it is to remember. And actually, I love sausage pizza, so I don't really want you to throw any of mine away, especially. From a communication perspective, I want to address this statement that each layer adds information to the packet. And I wish I could go back to that encapsulation, de-encapsulation slide. I can't, but you can as you're watching the videos, and just take a look at that again, because basically in terms of a request from web browser to website, we would have a user that's sitting at their computer and using a web browser. You know, that web browser is not actually in the application layer, but it interfaces with the application layer. And it uses protocols there to develop a request in HTML and to, or the browser puts the request in HTML. It uses HTTP to pass the request from the web browser to the web server. What we don't realize, and how fast this happens especially, is from my browser, it goes down through these different layers outlined in the OSI reference model. Okay, application, presentation, and session, they all add their unique pieces of information, and the packet just gets a little larger and larger with basically each layer adding information that's relevant to that layer. Transport is going to do a couple of things like breaking up the packet, sequence numbers, error checking, etc. Network layers about addressing. We'll go into this in more detail. Data link layers about breaking it up into the actual physical frames and then putting them on the physical layer. Okay, now picture this packet going from the physical layer at the source to the physical layer of the destination system. That may not be one from, point A to point B. That might be point A to point F through a number of different points, right? I mean, we can take 20, 30 hops sometimes before we get to another site. Usually it's roughly, anywhere from about 7 to 15 stops along the way. But let's just picture from source to destination. So the packet here has the web request from the web client to the web server. Once the packet gets to the destination, it works its way back up this reference model, de-encapsulating the information that was added by the source sender. Okay, and so from the perspective of two devices communicating, there are going to be multiple pieces that are added at the source that are then removed at the destination. At the data link layer, it's just addresses. It's, hey, is this your MAC address? If it's not, then this isn't for you. Drop it. This is your MAC address? Oh, this packet's for you. Then it goes up to the network layer and it looks at the IP address. Is this my IP address? If it's not, I must be a router and I'm going to be passing the packet again along, that'd be sort of those middle hops. But let's say it's mine. This is on the web server. Oh yeah, that's my IP address. We pass it up to the transport layer. The transport layer is piecing together multiple packets that are received and it's passing it up to the web service on the web server. And then the web server is going to do what? It's going to package the request and send it right back. And yeah, it is amazing how fast we get to these sites. Now, of course, we've got caching and things like that. You may not be completely loading a site every time, but even when you do, what does it take? 5 seconds on a high-speed internet connection on a site that's got a bunch of media on it? Probably not even that long. I mean, it's amazing. So, as I said, just conceptual. Don't get too hung up. We're going to talk about each layer. You want to know what's happening at each layer. You want to be able to recite the layers, and then we'll come back to this, as we go throughout. There will be times when we come back to it. And another big time is network devices. Knowing what layer of the OSI reference model a network device operates on helps you to know exactly what its capabilities are. That's another little trick that we'll learn along the way. All right, so let's talk a bit more about what these layers do. The application layer is an application's interface with network services. It's not the applications themselves. So we want to kind of throw that out. I think I already mentioned that, but it's not going to be the applications themselves. It is the protocols that those applications use to interact with the network. So the application, in many cases, let's just say is a web browser or an email client. Well, the web browser is using HTTP, Hypertext Transfer Protocol, which is a protocol in the application layer. The mail client may be using HTTP or POP, IMAP, more kind of historical email protocols, or SMTP in conjunction with those to send mail. Web browsers would be using DNS, but so would File Explorer, and just your Windows network client's going to use DNS. Telnet would be a remote administration using command line. That's fairly older, but SSH would be a more modern version of that. Anyway, those are all application layer protocols. They're protocols that are defined at that application layer that individual applications themselves can then interface with to interact with the network. Presentation's all about presenting the data. Okay, so it's putting it in a form that's going to be understood. This can include security information, encryption, compression for data. The session layer is all about establishing and controlling data communication between applications that are operating on different computers. Okay, so a web client and a web server will establish a session. They will often establish a session using SSL. So it's a secure session that has encryption keys that are used to encrypt and decrypt the traffic between the two. It also maintains that session. If I disconnect and come right back in, it remembers who I am, maybe, and I pick back up into that session. That's all stuff that happens at that layer. The lower layers probably do the bulk of the work from a networking standpoint. The transport layer divides long communications into smaller packages, also known as fragments. Transport layer also handles error correction and acknowledges the receipt of data. There's a number of things that happen at the transport layer. Segmentation is that fragmentation, if you will. Anytime you're breaking one piece of data up into multiple packets, well, then we're going to need to know how to put those back together. Now, in a perfect world, they'll show up packets 1 through 10 in that order. The internet is not a perfect world, so they will frequently not show up in the correct order, and therefore sequencing numbers are used to be able to put the packets back together at the destination. If you think of, just quick side note, if you think of the maximum transmission unit, MTU, on an Ethernet frame of being 1.5 megabytes, okay, 1500 kilobytes is what it is, so 1.5 megabytes roughly, that's not a whole lot of data. So your typical web request are going to be hundreds of packets, thousands of packets potentially that get sent back. So those are going to be sequenced. Also, the functionality provided at that layer is acknowledgments, being able to have the destination system say to the source system, yeah, I got that. So just so you know, checksums to validate the content of the individual packets, all of those things. That's at the transport level. Remember here, high level, guys. High level, probably what's in bold is really what is important. Not going to see a ton of questions on OSI. The network layer addresses data messages and handles message routing. So the network layer is all about getting the packets from source to destination. MAC addresses, also known as physical addresses, don't change. Those are on the NIC. They're on there permanently. So it's the protocol addresses, the IP addresses that will change. And we're going to need both, because the MAC addresses are going to be used to define the next hop, as we'll see later, and the protocol addresses are going to be used as the ultimate source, ultimate destination. Packets at the network layer are sometimes called datagrams, but that's just a term that's used for them there. At the data link layer, it packages bits of data from the physical layer into frames and then transfers them from one computer to another. It's using that Ethernet header, data section, and footer. The data section is going to have all of the added data from the upper layers in it already, and then the data link layer is creating that frame, that structured package where, okay, here's what's in the first part. It's always the same, different addresses. The data part is not necessary unless the address is your address, and the CRC at the end is just to validate the frame itself. So data link layer is about packaging and placing data on the physical layer and then getting it off. Physical is all about just transmitting bits from one computer to another. It regulates the transmission stream. It goes with physical connectivity devices, obviously, but its sole job is to transfer zeros and ones from one computer to another that represent these packages. And so I realize that that's a lot. That's a lot to take in. The OSI reference model is listed on the standard, so let's just, like I said, try to keep it simple. I've given you a lot of information. It's probably more information than you'll need from a test perspective, but that's not all we're about. I'm trying to teach you as much as possible about computer networking as well. And so OSI reference model is a standard that has been out there since the 70s, and it's still how we relate a lot of things from a conceptual basis. We'll talk about TCP/IP. And when we get into individual layers and protocols and exactly what's involved, it's probably more likely to get questions from TCP/IP than the OSI-RM. But TCP/IP essentially is just what the OSI reference model is, in that it defines that layered approach to networking. So know the layers, know the names, know the general in bold, what's there. Probably will see a couple questions, and you'd like these to be easy ones for you. All right, in this chapter, we looked at network fundamentals. We got you started with an introduction to networking, just understanding the purpose of a network, the various components, the types of networks that exist. We looked at the network models, work group versus domain, and discussed the advantages that domains have, especially for larger organizations, of centralized management and centralized security. We talked about physical and logical topologies, how the network is physically laid out versus how data logically flows. We discussed a number of different network components and services, just kind of in general, but giving you an idea of some of the capabilities that are available out there on today's networks. And then we talked about the importance and development of network standards. Got you introduced to Wi-Fi standards, to some of the standards organizations, the Ethernet 802 and 10-base standards, and exactly what that means. And as I said in that part, I know we went kind of quick. We weren't delving into the details. If you've looked at the objectives, for instance, you see that, well, wait a minute, there's a lot of 10-base standards that we didn't hit. Very next chapter, we're going to be dealing with cables and connectors, and so we'll discuss in more detail at that point. But network standards are very important because they provide us with interoperability between different vendors.